Hi students. So as many of you guys recall, yesterday we looked at the phases in the phase diagram. And so we know that there are three states of matter: solid, liquid, and gas. And so in this chapter, we're going to spend some time getting to understand, getting to know each of these different states of matter. And then in our next chapter, we're going to take an even closer look at gases. So we're going to begin by talking about gases. Gases are the state of matter with the highest energy. An important thing to remember about energy is that energy typically comes from temperature, or heat comes in as energy is given to the molecules. So the hotter they are, the more energetic they are. So it makes sense then, it stands to reason that solids would have the least amount of energy, liquids, and then gases, because as you go from solid to liquid to gas, you're increasing in your temperature. So gases are the highest energy state of matter. They also have the most space in between the molecules. When you picture a gas, you should be picturing tiny molecules like little ping pong balls or pebbles soaring, zooming through space. Very small in relationship to all of the space that is around them. And so because of that, they have a lot of space between them, which gives them compressibility. Also, because of their high energy, those molecules are going to be moving very quickly. Energy is kinetic energy in this chapter. Kinetic energy is the energy of motion. So whenever we say energy, we're talking about kinetic energy, which is really how those molecules are moving. They have more space, they're able to move fast. This also makes them compressible. So something that's compressible has to start by having lots of empty space. If you wear a down jacket like this one that I'm wearing, they say that they're very packable. What that means is if I were to fit this jacket into my bag, I was going to go somewhere, it would shove into the bag just super easy. They're very packable. And actually, some of them come even with like a little stuff sack that you can put the jacket in and keep it in just like a little tiny pocket, like it could go in your car door or in your purse. This is said to be compressible, but in order to be compressible, you first need to have lots of empty space. So it stands to reason then that this jacket probably has lots of empty space on the inside, and we know that that's true. It's a down jacket, it's full of feathers. Feathers are warm, but they are mostly empty space. So gases have the highest energy, the most space between the particles. They're the most spread out. They move the fastest. And because of all of these things, we also say that they are the most compressible. So when we discuss gases, there are many conditions that affect how a gas behaves. If we have it at a really low temperature or a really high pressure, we can change or convince the gas to behave in a non-predictable way. So when we discuss gases, we have to be very clear about what kind of gas are we talking about. And so the term we use here is an ideal gas. An ideal gas is imaginary, much like an ideal student or an ideal child. You can have an ideal, but reaching it is pretty difficult. An ideal gas perfectly fits all of the assumptions of the kinetic molecular theory. And so you might be thinking, well, what are the assumptions of the kinetic molecular theory? And don't worry, I'm going to take you through those on the next slide. But for now, we just know that an ideal gas is perfect. It perfectly adheres and obeys all of the rules and parameters that we put on a gas. They're not real. Real gases are something you'll also hear mentioned. A real gas is a gas in real life as it actually is behaving in the real world by observation. So an ideal gas is like a prediction, where a real gas is an observation. And just as a reminder, the kinetic molecular theory that we're talking about is the theory that all particles in all matter are always in motion. Kinetic, remember, means motion. So the kinetic molecular theory is the theory that molecules are in motion all the time, all molecules, everywhere, no matter what. So now it's time to get to those assumptions of an ideal gas. And remember, these are the assumptions that an ideal gas perfectly complies with. The first is that gas particles are small hard spheres with an insignificant volume. What this means is that gas particles, compared to the space that they're in, they're just so small, they're insignificant. It would be like if you were a single person in a whole football stadium, or a single person or a small group of people in the whole Yosemite National Park. You are so small in relationship to that space that you being there is actually insignificant. You are not affecting the space by existing there. So a particle in a gas is meant to be a small, hard sphere with an insignificant volume. And so it's important to note here that gases are much farther apart than they are in the liquid or the solid state. And what this essentially means for us is that a container of gas is mostly a container of empty space. The second assumption of the kinetic molecular theory for ideal gases is that the movement of the particles are rapid, constant, and random. This is important. The gases are moving as fast as they can, but in no particular direction. Okay, if I throw a baseball to you, you should be able to catch it because you can predict the motion of that baseball. That's not how a gas travels. A gas motion is random. It may be traveling towards you and then turn right or drop down or bounce or swirly around. The gases can move in any direction. They're just rapid, constant, and random. The most important thing is that they never stop and that they have random motion. The third assumption of an ideal gas based on the kinetic molecular theory is that gas particle collisions are elastic. So when you think of the word elastic, you might think of a rubber band or a bouncy ball. And an elastic collision is a collision with no loss of energy. I think it's helpful before we think about elastic collisions to think about a perfectly inelastic collision. Car manufacturers, car makers try to make their collisions perfectly inelastic, not elastic. What that means is they want, when two cars run into each other, they want the collision to end there. They don't want those cars bouncing off and sliding into other cars, hitting light posts, crashing into buildings, causing car pileups. The idea is that when two cars hit each other, there's actually even mounts put on engines that are supposed to break free and drop the engine down to the ground so that the engine grinds against the cement in order to keep the car anchored. They want all of the energy of the collision to exist in the crumpling of the engine compartments. Now, this totals cars. So cars that get in a car accident now are more likely to be totaled than cars that were manufactured in the 1950s. But when those cars hit each other, they are less likely to involve other surrounding vehicles or people because their collision is perfectly inelastic. It's absorbing all of the energy into the crash itself. Now, gas particles are meant to collide in exactly the opposite way. When two gas particles come in and collide with one another, they are meant to bounce off of each other with exactly the same amount of energy, the same velocity, the same speed as they entered the collision. No energy lost. That means the collisions will go on forever. They will never stop. If you think about that in terms of cars, that would be really bad, right? Imagine two cars crash into each other at 60 miles an hour, and then they bounce off of each other at 60 miles an hour, and then they keep bouncing and colliding with everything else around them, and they just keep gaining energy like Flubber, like the Nutty Professor. They just keep bouncing off of each other, gaining energy, gaining energy, gaining energy. This would be really bad for cars and freeways and driving and humans for that matter. But for gases, it's good. So their collisions are perfectly elastic, no forces of attraction, no loss of energy. So these are the three assumptions of an ideal gas. These have implications for what we know about how a gas behaves. I know that if I have a container of gas, it's going to have a low density. It's going to feel light compared to solids and liquids. I know that the gas particles are moving, that they're moving quickly, that they're bouncing off of each other, and collisions are basically a given in gases. And that's important too, because collisions are what are going to cause pressure. And pressure is how we measure what a gas is doing. So we can take for granted that all gases are going to be having these collisions because they have rapid, constant, and random motion. And their collisions are elastic, so they'll never run out of energy. All of this depends on the temperature. So temperature, heat, is energy. And so the heat of the container gives energy to the particles. The more heat they have, the faster they move. So a cold gas moves slower than a really hot gas, and a cold liquid moves slower than a hot liquid. So as we increase in temperature, we are increasing in the energy, which means the speed, the velocity of the particles. So we're only interested in their average energy. Any specific particle could be moving faster or slower than the average, but every gas has an average energy, and that energy is actually constant no matter the gas. So the energy that they're putting into movement is solely based on their temperature. So those assumptions of an ideal gas lead us to the application of the kinetic theory of gases. So that list of 3 kind of goes with this list of 5. And I want you to be thinking as we're going through them, how do they connect? And I'll try to help you connect those dots a little bit as well. First, gases expand. Gases will expand to fill any space that they're in. And this drawing down here is showing this. So we have a gas that is contained in 1/2 of this container. And these particles are moving, they're colliding with the container walls. Their motion is rapid, constant, and random. When we remove the divider, these gas particles will begin to move, to spread out, to expand, and eventually they're going to fill the entire container. This is easiest recognized with a fart. If someone farts on one side of a room, that fart expands until it fills the room. So at first, just the person who cut the fart smells the fart. And then slowly the people around them can smell it. And that's where the first one who smelt it dealt it concept comes from. Although that's a lie, because obviously the first person isn't going to say anything because they know they farted. Anyway, as the fart continues to spread across the room now, though, eventually you see the look on people's faces like, I smell fart. And that continues across the room until it reaches everyone. And then eventually it feels like the fart smell just goes away. But it doesn't. What happens is those fart particles, which is really sulfur and methane, they're just gases, but those gas particles continue to expand until they're filling the whole atmosphere. But when they're filling the whole atmosphere, they are insignificant. Remember, they have the small, hard spheres with almost zero mass. By the time they fill the whole atmosphere, that single sulfur or methane particle is so small that it's insignificant. We can no longer smell it. So we can only smell or detect a chemical at a certain concentration. So they have become less concentrated. Similarly, these gases are flowing past each other. So because their motion is random, there are no forces of attraction, their collisions are elastic, these gases are able to move past each other without any hindrance, without any impedance. They're not held back. Both gases and liquids are said to flow, and they are considered to be fluid. Because gases are so far apart, we're back to that first assumption that the gases are mostly empty space. That would mean that a gas is going to have low density. So density is mass over volume. Density equals mass over volume. And so the more space you have and the smaller your mass is, the lower your density is. And so we expect things that are made of gas or mostly gas to feel light, to lift up, to not be very heavy for how large they are. Think of a balloon. A balloon is mostly empty space. A balloon is mostly gas. And so for that size, a balloon is very, very light. If you compare that to a medicine ball or a kettlebell, those things are very, very dense. They have much more mass in the same amount of volume. So they have a much higher density because gas particles have a low density. They will also have a high compressibility. Compressibility is your ability to squish it down. We already talked about that with the jacket, right? Packability. So because they have a low density, because they have so much empty space, I should be able to compress or squish something made of gas down into a smaller volume if I want to. That's what we do in our propane tank. Remember, I've been talking this whole time about how gases are light and they have this low density. But if you have ever picked up a propane tank, you know that they are heavy when they're full. And that's because the gas is compressed into the propane tank. The same is true of a helium tank, like for blowing up balloons. Helium tanks are full of compressed gas. The same thing is true of like a dust off, like to clean your computer. So those are compressed gases, and those gases are under pressure, right? They have been squished. They're under high pressure. The last application is that gases are able to diffuse. And this one comes back to the rapid random motion. This comes back to the elastic collisions. This comes back to expansion. It's just kind of an extension of expansion. So if we look at these two containers, this one of the blue gas and this one of the red gas, and at the beginning, the barrier or the stopper between them is closed. And then we open this stopper. Due to the random motion of the gases, the red gas is going to expansion. The red gas is going to expand over into this canister. And the blue gas is going to expand over into the red canister. And that process causes the mixing of the two gases, which is what diffusion is defined as. So the mixing of the two gases through their random motion. So we get this diffusion. So these applications of a gas come from the assumptions of the gas. And all of this wraps up into a picture where you should now be able to start to predict what a gas is going to do under certain circumstances. And if you're doing that, then you are applying the kinetic molecular theory of gases to ideal gases. So great job. You've totally got it.